Recursion is a programming technique where a function calls itself to solve a smaller piece of the problem. Think of a set of Russian nesting dolls. To open the biggest doll, you first open the smaller one inside and so on until you reach the tiniest doll that cannot be opened any further. The tiny doll is the base case, the point where the process stops. In mathematics, recursion is tightly linked to mathematical induction. Induction proves that a statement holds for all natural numbers by showing two things. First, it is true for the first number, the base case, and second, if it is true for an arbitrary number k, then it is also true for k plus 1, the inductive step. The inductive step mirrors the recursive step. A problem for n is reduced to a smaller problem for n minus 1, and the correctness of the smaller problem guarantees the correctness of the larger one. When we write a recursive factorial function, we must explicitly describe two parts. Base case, the simplest input that can be answered directly without further recursion. For factorial, the definition tells us that 0 factorial equals 1, and also 1 factorial equals 1. This stops the infinite chain of self-calls. Recursive case, how to break the current problem into a smaller subproblem. For any integer n greater than 1, the factorial is defined as n multiplied by the factorial of n minus 1. In code, we express this as return n times factorial of n minus 1. The formulation follows the mathematical definition directly and ensures that each call gets closer to the base case. The key is that every recursive call must move the argument toward the base case, otherwise the function would never stop. The factorial function is defined for a non-negative integer n as the product of all positive integers up to n factorial equals 1 times 2 times 3 times. If we separate the last factor n from the product, the remaining product is exactly n minus 1 factorial. N factorial equals n times 1 times 2 times n minus 1, which equals n times n minus 1 factorial. This equality is called a recurrence relation, because it expresses the value of a function in terms of its value at a smaller argument. Some useful properties. Uniqueness, the recurrence together with the base case 0 factorial, equals 1 uniquely determines n factorial for every n. Growth, factorial grows faster than any exponential c to the n Stirling's approximation. N factorial is approximately square root of 2 pi n times open parenthesis n over e close parenthesis raised to the n. Divisibility, for any k less than or equal to n, k divides n factorial because k appears as one of the factors. These properties are often used in combinatorics, for example counting permutations, and help us reason about algorithmic correctness. Hash include stdio.h. Factorial returns n factorial for a non-negative integer, and the function is recursive, it calls itself with a smaller argument. Unsigned long factorial int n. Base case 0 factorial and 1 factorial are defined as 1. If n less than or equal to 1, return 1 unsigned long. Recursive case n factorial equals n times n minus 1 factorial. Return unsigned long n times factorial n minus 1. Close brace. Int main void. Int n equals 5. Print d factorial equals lu newline with n and factorial n. Return 0. Close brace. Unsigned long is used to hold larger results, but even this type overflows quickly, e.g. 21 factorial exceeds its range. If n less than or equal to 1 statement is the base case, without it the function would call itself forever. Return n times factorial n minus 1 line is the recursive case that reduces the problem size by 1. Call factorial 4. N greater than 1 returns 4 times factorial 3. Call factorial 3. N greater than 1 returns 3 times factorial 2. Call factorial 2. N greater than 1 returns 2 times factorial 1. Call factorial 1s. N less than or equal to 1 returns 1 base case reached. Factorial 2 returns 2 times 1 equals 2. Factorial 3 returns 3 times 2 equals 6. Factorial 4 returns 4 times 6 equals 24. Call stack picture top equals most recent call. Stack frames from top to bottom factorial 4, factorial 3, factorial 2, factorial 1 base case. When the base case returns the stack, unwinds each pending multiplication, is performed in reverse order, finally giving 24. Explanation: the recursive factorial makes exactly one recursive call for each integer, from n down to 1. Time complexity - the function performs a constant amount of work, a comparison and a multiplication at each level, and there are n levels. Hence the running time is big O of n. Space complexity - each recursive call adds a new activation record, local variables, return address to the call stack. The deepest stack depth equals the number of calls, which is n plus 1 including the base case. Therefore, the auxiliary space used is big O of n. This space is not counted as memory for the result, but as extra memory needed for recursion. An iterative version could achieve big O of 1 space. When writing recursive factorials, beginners often stumble into 3 classic problems. Missing base case: if n less than or equal to 1 test is omitted or incorrect, the function never stops calling itself, leading to infinite recursion and eventually a stack overflow. The program crashes because the call stack exceeds its limit. Stack overflow: even with a correct base case, a very large n, for example 100,000, will create a deep call stack that exceeds typical system limits, often a few thousand frames. The solution is either to use an iterative loop or to increase the stack size, not recommended for exams. Integer overflow: factorial grows extremely fast. 13 factorial equals 6,227,020,800 already exceeds a 32-bit signed integer. Using unsigned long pushes the limit to 20 factorial, approximately 2.43 times 10 to the 18th, but 21 factorial overflows even that. In real programs, you must either check for overflow, use arbitrary precision libraries, or limit the allowed input range. Remember, recursion solves the logical problem. The practical limits, stack depth and numeric range, must be handled separately. Explanation: typical exam questions on this topic include: write the recursive function, write a C function int fact int n that returns n factorial using recursion. Include the base case. Students must produce the correct if test and the return n times fact n minus 1 line. Trace the execution, show the value returned by each call when fact 3 is executed, and draw the call stack diagram. The answer should list the sequence 1 to 2 to 6 and a stack with 3 frames. Complexity analysis: state the time and space complexity of the recursive factorial function and justify your answer. Expected answer: big O of n time, big O of n space, with explanation about 1 call per integer. Identify the bug: what will happen if the base case is written as if n equals 0, return 0. Explain: the function will return 0 for any n greater than 0 because the recursive multiplication includes a 0 factor. Compare with iteration, rewrite the factorial using a for loop, and discuss which version uses less memory. The iterative version has big O of 1 extra space. These questions test understanding of the concept, ability to implement it correctly, and awareness of its limitations.